Welcome back, student. Now today we'll discuss on pressure distribution and choking in a nozzles. In the previous lecture video, we already discussed on the dimensional velocity. And now today we'll discuss on pressure distribution and choking in a nozzles. So what you see that in the diagram that, so this is a particularly, so this is a chamber or reservoir, you can say, okay, reservoir. So this is the reservoir in which the fluid is stored here, and the fluid, when fluid is stored, that fluid is basically resting condition. Okay, the fluid is rest is condition, and the at that time the stagnation pressure is basically defined as P0, velocity is V0, density is like rho 0, T0, and all these terms basically this is basically the stagnation properties, right? Now when the fluid is flow through a particular, this is a convergent channel in which the fluid is flow through these channels or duct, you can say that. Now this is the one type of chamber, you can say, and this is a exit plane or exit duct section, exit of the duct section. Okay, now this is one type of arrangement where the fluid is flow through a particular outside of the channel, outside of the duct, and there is a one valve are there. So this is a valve, okay, and the atmospheric pressure designated with the P atmosphere. And when the valve is totally closed, okay, when the valve is totally closed, so there is no flow in between the total conduct, total duct, so that they will produce a particular back pressure. So okay, they will produce a back pressure that is called basically PB. Okay, now corresponding to this, we just observe that pressure distribution within this nozzle or duct. So if you draw a pressure and with the corresponding length of the duct, you can say that this is the pressure, this is the L, P versus L plot. Now this is a P L plot in which we can draw. So this is, if you draw this section, so this is basically exit plane. So this is the exit plane of the duct. If you draw a particular line, that basically exit plane here. Okay, now if you open the valve slowly, okay, if you open, this is the closed position, so there is no change in between back pressure, exit pressure, as well as stagnation pressure. So both are actually same. This is basically, that's why it is horizontal, there is no change. Now when the valve is slowly open, the, or you can say that reduce the back pressure, that basically when you reduce that, so this is basically when you reduce that, the diagram shows that PB1. So PB2, if you reduce, that will be reach up to PB1 state, and that will be equal to PE. When PB reduce, obviously there are some mass of flow of fluid, there will be flow through the particular channel. So at this particular PB1, there are some mass flow rate will be occur, some mass fluid flow rate will be occur. Similarly, if you reduce again, or if you slowly close the valve again, it reach up to PB2, which is basically less than PB1. And when you reach with PE, obviously there is some mass of fluid that flow through the particular duct sections. But when you again slowly open the valve, at particular when you reach with PB3, if you reduce the valve along the length axis, along the length of the duct, if you reduce the pressure of the back pressure, that when you reach PB3 and when it reach with the pressure exit plane, when two values are meet together at a particular corresponding values of that, it will reach at a particular P star values. Okay, you know that P star basically the ratio when we reach actually Mach value. So Mach number is equal to 1, or Mach number is equal to 1. That means velocity of the fluid that equal to velocity of the sound. And as you know that P star by P0 is equal to gamma plus 1 by 2 divided by gamma divided by gamma minus 1. You know that P star is basically the properties or the pressure at a particular throat section or the maximum sections where the maximum mass flow rate occurs, and P0 designated as your stagnation pressure. So, okay, now V star basically, as you know that under root of gamma T, when you reach P star, V star, that will be T star, that equal to C star. So V star will be C star when M is equal to 1. When M is equal to 1, when PB just reduce that, reach up to a particular level, that is basically PB3, when it is equal to PE, when it is equal to P star, at that particular conditions, they will reach a critical pressure ratio. At that particular time, flow will be maximum. Okay, now if you draw a diagram with corresponding velocity with respect to length of the drag. Now, suppose this is the velocity. When you reduce the pressure PB1 from the level PB to PB1, so there are some atoms of velocity that is basically you can say that is V1 level corresponding to PB1, right? If you reduce the pressure from PB to PB1, it will attain a particular velocity that is basically V1. Again, if you reduce the pressure by slowly opening the valve, it reach the if it reach the PB2, that corresponding velocity will be V2 because velocity is increased because of the flow velocity is increased here. That's why V1 to V2. Again, if you reduce PB, again if you reduce the value of PB means back pressure by means of reducing the flow. If you increase that pressure, that velocity will be also increased, and that will be equal to the velocity of sound. So velocity of fluid is equal to velocity of sound when P is reached to the P star, and at that particular time Mach number is basically 1. So at that particular region, the velocity is maximum, and obviously the mass flow rate also maximum. Okay, and this is the basically the pressure distribution and choking in a nozzle part. Now if you decrease the if you increase the PV value, below critical pressure. Now suppose this is your critical pressure limit. Now if you increase the if you when PB is increased, okay, below the critical pressure, so this is the critical pressure limit. If you increase the pressure limit PB and below the critical pressure line, that is basically indicated here 4 line. If you indicated here 4, and there is no increase in the mass flow rate, so in this particular region there is no mass flow rate and P remains constant at a value equal to critical pressure. Okay, and ME is equal to 1, and so the drop in pressure from PE to PB outside the nozzle exit. So this is the choking limit, which means that for a given stagnation condition, nozzle is passing the maximum possible mass flow. So this is the pressure distribution and choking in a nozzle part only for the convergent nozzle. If we concentrate on the convergent divergent channel, like this is a convergent and divergent channel in which you can say that this is the reservoir in which fluid is stored. Now if fluid is flowed through a particular channel or duct, you can say that now this is the throat section, this is the throat section, this is the convergent section, this is the throat, and this is the divergent sections. When fluid flow through this channel, okay, and if the valve is, so this is your valve, when the valve is closed, so there is no back pressure, means their back pressure is basically 100%. Okay, now if you release the valve, slowly, so back pressure will be decreased, so from the level PB to PB1, again PB2, again PB3. So corresponding to PB1, PB2 and PB3, there are some pressure and velocity changes. When the back pressure reach from PB to PB1, when you reduce the valve, when you open the valve and the pressure decrease, back pressure decrease from PB to PB1, the pressure basically when the fluid is flowed through a particular convergent channel, the fluid pressure will be decreased. So this is the convergent section, this is the fluid pressure will be decreased and velocity also increase. When the fluid is flowed through a particular throat section, they will reach a particular pressure decrease maximum. Okay, maximum pressure decrease will be occur. Again, when fluid is flowed through a divergent section, pressure will increase. Okay, and velocity also decreases. Okay, so for the pressure level PB1, again for PB2 case, again for the PB2, same incident will be happen. Now if you reduce again the back pressure, if you slowly open the valve at when it reach at a particular level, that particular level it reach that particular M is equal to 1. That means P means pressure, back pressure is basically reach with the critical pressure ratio. Okay, and this is the critical pressure ratio when it reach, and the maximum mass flow rate will be occur for these sections. Okay, So this is the section at which the maximum mass flow rate will be occurred. Now, if you say there's, suppose this is your PB4, okay. Now, point 4 basically indicate, and point 3 means at PB3 basically indicates the back pressure at which actually M is equal to 1 at the throat, but the divergent section act as a subsonic diffuser in which the pressure increases and the velocity decreases. Okay. Now, point 4 basically a point which indicates other back pressure for which the flow is isentropic throughout, and the divergent section act as a supersonic nozzle. So these are divergent section which act as a supersonic nozzle at a particular condition. Now, if you increase the velocity, beyond PE4, or you can say PB4, that particular condition is basically called as the design pressure ratio, and that design pressure ratio also designated with PBD. When it reach that, now if the pressure is lower to if this pressure is lower to the section like this one, suppose this is your design pressure line, if you decrease the back pressure here, or if you increase the back pressure from design back pressure to this limit, so in this particular limit or region, so there is no further decrease in exit pressure occurs, and the drop in pressure from PE to PB, okay. So outside the nozzle, so between the back pressure designated by points 3 and 4, so this is the point 3 and 4, there is no pressure limit, and when it is happens, so there is actually back pressure will be provided, and there is a chances when it reach to the mid particular channel, when you reach to this particular channel, when you meet, actually there is shock is provided. And similarly, when this point is here below this design pressure line, so when you have to meet this particular line, so there will be produces shock, okay. That shock basically called natural shock, okay. That is called basically normal shock, okay. And basically shocks are basically two types: normal shock and oblique shock. Now we'll discuss on it in the next lecture video, okay. Now let us take a numerical on compressible fluid flow. The numerical basically is given that the air is flow, okay, air is flow through a particular duct or any type of convergent divergent nozzles. The condition is given, okay, the condition is given like the pressure, temperature and Mach number is given. Now as you know that pressure, the normal pressure is given as P. As you know that pressure is basically here, it is P is equal to 320 kilopascal, it is given. Now temperature is 300 Kelvin is given, and Mach number, as you know that M is basically 0.6 that flows through a particular duct. You know that what is duct, and duct basically it may be a nozzle or diffuser, and it may be a nozzle or diffuser, convergent divergent, okay. So the air is flow through a particular convergent divergent duct like that. So the condition is given in the numerical. Now you have to calculate or determine the velocity. The velocity basically, you know, the actual velocity or velocity of fluid, that is basically indicated as small v or capital V. And stagnation temperature, as you know, the temperature basically designated with T term. Now stagnation temperature is basically designated with T0, okay. And stagnation pressure also, stagnation pressure, that is basically P0, and density. So you have to calculate the velocity of the fluid, you have to calculate the stagnation temperature, stagnation pressure and density, okay. You have to calculate all these terms. Now what are the value are given? So the value are given that the pressure is given as 320 kilopascal from the numerical. The temperature is 300 Kelvin. The Mach number is 0.6. So Mach number 0.6, it suggests that if you know that if the Mach number's values is less than 1 or greater than 1 or is equal to 1, if Mach number value is equal to 1, that means the velocity or the flow is basically sonic flow. If the Mach number is less than 1, that is called subsonic flow. If M value is greater than 1, that is called supersonic flow. Now the value of M is here given as 0.6. That means the flow, that air is flow through a particular duct, that flow basically a subsonic flow. Now value is given 0.6. Now we have to calculate all those things. Now as you know that sonic velocity, the sonic velocity is related to be C. Now C for when you calculate C, and you know that for in ideal flow, that we will assume that that basically the flow basically reversible and adiabatic process, in reversible adiabatic process means isentropic process. In isentropic process, the velocity or sonic velocity you can calculate, that is basically under root of gamma RT, where gamma is the basically the Cp by Cv, R is the gas constant, and T is the temperature. So gamma for air, that is 1.4, R is 0.287, and T's value is 300. Okay. Now, if you put these values, you can get the sonic velocity like 347.2 meter per second. Now, you know that Mach number. That Mach number is designated with m. Now, m is the ratio between velocity of fluid divided by velocity of sound. So, velocity of fluid is v and velocity of sound is c. Now, m is equal to v by c. When you calculate v, so v is equal to c into m. So, c into m. Now, value of m is given, that is 0.6, and value of c, that is coming out 347.2 meter per second. If you multiply with m into c, you can get the velocity of fluid, 208.3 meter per second. Okay. Now, next, so you have already calculated the velocity of sound. Okay, velocity of sound. Now, you have to calculate the stagnation temperature. Stagnation temperature, as you know, that designated with T0. Now, relationship with the stagnation temperature to the static pressure or static temperature is basically T0 by T is equal to 1 plus V square divided by 2 into Cp into T. Okay, so T0 will be T will be in the upper side, T0 equal to T plus V square divided by 2 into Cp. Now T0 equal to T value of T is given, that is 300 Kelvin. V is the velocity of the fluid, that is basically coming out 208.3, right? And the 2 into Cp value is given, that is 1.005 into 1000. It is converted into 4 meter. Okay, that answer will be for stagnation temperature T0 will be 321.9 Kelvin. Now, so this stagnation temperature, now we have to calculate the stagnation pressure. As you know that the relationship, the stagnation temperature to stagnation pressure, that is basically T0 by T is equal to P0 by P to the power gamma minus 1 by gamma. This is the normal temperature pressure relationship in case of reversible adiabatic process. Just we apply in this case. So T0 by T is equal to P0 by P to the power gamma minus 1 by gamma. Right. Now, as you know that, so from this equation, you can calculate P0 means stagnation pressure. So P0 is equal to P into T0 divided by T to the power, that will be reversed. So gamma to the power gamma minus 1. If you put these values P, like the pressure that is given as basically 320 kilopascal here, and T0 is stagnation temperature, that is basically 321.9, and T and 300 Kelvin. If you put this value and gamma for air basically 1.4, then you can calculate the pressure or stagnation pressure, that is 4010.5 kilopascal. Now, the last part of the numerical, that basically the density of air. When you calculate the density of air, that means you know that that for any gas, for any ideal gas, that basically follows the equation, that is P is equal to RT. It can also written as P is equal to RT. P is equal to RT. It also written as P by rho is equal to RT, because V is equal to 1 by rho, right? So rho is equal to P by RT. It also written in this fashion. So rho you can write as a P by RT. Okay, P by RT. So for these equations, P is equal to rho RT. From this equation, P is equal to rho into R into T. You can calculate the value of rho. Rho is equal to P by RT. You can, if you put these values, P is equal to 320 kilopascal, R is 0.287, and the temperature is 300 Kelvin. You can get the value of density, that is coming out 3.71 kg per meter cube. Okay, so this is the numerical. You can try yourself for another numericals. Okay, and we can discuss in the next lecture video in normal shock, basically in in ideal gases. Okay, in the next lecture video. Okay, thank you very much for listening me and for watching me. Goodbye.